Good morning, good afternoon, and good evening, everyone. Dear authors and invited guests, welcome to Technical Session 12A. I'm Sanskriti Khamkar, and I will be moderating this session. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it is my pleasure to welcome you to the last day of the 11th International Congress on Information and Communication Technology, that is ICICT 2026, in London, UK. I hope you find today's session engaging, informative, and insightful. In this session, we have 6 presentations. Each presenter will have 12 minutes for their presentation, followed by 3 minutes for question and answers. I will give a gentle reminder when 2 minutes remain. I request all participants to stay connected until the closing remarks. If you have any questions or updates, please feel free to share them in the chat box. I'd also like to apologize in advance for any mispronunciation of names during this session. Before we begin, I would like to introduce you to our session chairs. First, we have Dr. Vidula Meshwaram, who is an assistant professor in the Department of Computer Engineering at Vishwakarma Institute of Technology in Pune, India. She has 19 years of professional experience with expertise in assistive technologies, Internet of Things, machine learning, and computer vision, contributing actively to teaching, research, and academic innovation. Ma'am, would you please like to share a few words with us?
Yes, thank you, ma'am, for such a wonderful introduction. It's a privilege and honor to chair this session of ICICT 2026, and we would like to hear great knowledgeable sessions from the presenters. So I thank you all, the organizing committee and my co-session chair, for being present for this event. So thank you all, and look forward to a nice sessions and to hear from the participants. Thank you, ma'am.
Thank you, ma'am, for encouraging words. This session is also co-chaired by Professor Jamie Pulambarat, who is a senior academic and administrator at Bulacan State University in Philippines, holding the academic rank of Professor 6. He currently serves as the Vice President for Administration and Finance. His research interests lie in information technology and education, with a particular focus on data analysis of faculty productivity, machine learning applications for student performance, and the development of efficient office management systems. Welcome, sir. Would you please like to share a few words with us?
Okay, thank you, Ma'am Kamkar. Good afternoon and good evening here in the Philippines. It's my great pleasure and honor to be part of this conference and being part of this session. I will look forward for our presenters and good luck. Again, thank you so much.
Thank you, sir, for the warm welcome. Now let us proceed with the presentations. First up, we have Nada Adel, who's presenting a lightweight hybrid encryption model for secure EHR in IoT environments.
Good afternoon, everyone. I am Nada Adel from the Faculty of Computer and Information, Minofia University. I am pleased to present our work to you today. Thank you. I will share my slides.
Yes, please.
Okay. My work is titled A Lightweight Hybrid Encryption Model for Secure Electronic Health Record in IoT Environments. My agenda is introduction, related work, proposed work, experimental results, conclusion, and references. First, introduction. Nowadays, a patient's complete medical history can be stored digitally in an electronic health records instead of being kept on paper. Therefore, The main goal of electronic health record systems is to improve the quality of patient care, as medical data can now be easily accessed and shared from anywhere. This ensures faster decision-making and better coordination between healthcare providers. With technological advancements, everyday objects such as watches and devices have been transformed into smart tools capable of sensing their surrounding environments and transmitting data. So, the integration of IoT in healthcare has improved real-time access to patient data, but also raised major privacy and performance concerns. The use of IoT in healthcare improves real-time monitoring and access to electronic health records, but also introduces significant challenges in privacy and resources. Related works. These are the related works I worked on. First paper proposed a blockchain with attribute-based encryption approach that provides strong privacy and decentralized data sharing, but with high computational costs and limited suitability for resource-constrained environments. Second paper use AES with RSA, provide strong security and good key management, but consume high power and memory on IoT devices. Third paper use DNA-based cryptography, offers a high complexity and a large key space, but suffers from high latency and memory overhead with no strong key exchange mechanism. Proposed work. Methods like RSA and AES gives us strong security, but our resource consumption for IoT devices, especially with limited power and memory. To solve this gap, I propose a hybrid approach for securing electronic health records in resource-constrained environments. Hyper-encryption model for electronic health records combines SPEC for lightweight data encryption and RSA for strong key management, ensuring security in resource-constrained IoT healthcare environments. The following figure presents the framework adopted in this work for the hybrid SPEC with RSA encryption model. We will get through three phases. The first phase, key generation. First, generate a 32-byte random symmetric key. This is SPEC key. Apply a lightweight pre-processing formula to enhance key randomness with minimal computational cost. Encrypt the processed key using the RSA public key for secure transmission. Next, phase 2, data encryption. Convert electronic health records data into string format, then encode into byte and split into 60 byte blocks. Encrypt each block using SPEC in CBC mode to improve privacy and prevent repeating patterns. Phase 3, decryption. Decrypt the key at the receiver side using the RSA private key and initialize the SPEC cipher. Store the encrypted data securely. Results. Two datasets were used, a small-scale dataset and a larger real electronic health records dataset to validate model scalability and performance with increasing data volume. The first dataset from UCI repository, it includes 100 patients with 50 features. The second dataset, hospitalized patient with heart failure, it includes 2008 patients with 168 features. Both datasets include numerical, categorical, and text data types. The result was, although AES with RSA achieved faster execution time, the proposed spec RSA model shows significantly lower CPU, memory, and energy consumption. This results highlights the suitability of spec with RSA for resource-constrained, smart healthcare, and IoT environments. The table show our results. Here, execution time for EES with RSA was 8 seconds, but spec with RSA was 12 seconds. But CPU spec with RSA achieved the best result for only 70%, but AES achieved 20% in this case. Current memory, EES with RSA achieved 17 megabyte, but spec with RSA achieved 14 megabyte. Peak memory for EES with RSA achieved 19 megabyte, but spec with RSA achieved 18 megabyte. Energy consumption, also EES with RSA achieved 674, but spec with RSA achieved 404 megabyte. With the larger dataset applied, the result confirmed that the proposed spec with RSA model contain high efficiency not only with small datasets but also with larger. These figures summarize the result for the two evaluated datasets. Discussion. Spec with RSA achieves an effective balance between privacy and performance. The lightweight spec design significantly reduces CPU and energy consumption compared to AES with RSA. Combining RSA with CBC mode improves privacy through secure key exchange and reduce pattern leakage. But the slightly longer execution time of spec with RSA is due to the lower CPU usage, not weaker performance. With equal resource allocation, spec with RSA is expected to achieve comparable efficiency. We multiply the CPU usage of spec with RSA by its execution time. This gives us the actual processing load consumed by spec with RSA. Then we divide this value by the CPU usage of AES with RSA. to estimate how long SPEC with RSA would take under the same processing load. If so, the result is very small.
Excuse me, Ms. Nanda. This is just a gentle reminder that 2 minutes are left for your presentation.
Okay. Conclusion. A hybrid SPEC with RSA encryption model is proposed, combining lightweight SPEC encryption with CBC mode with RSA for secure key exchange management. SPEC with RSA achieved better resource efficiency than AES with RSA, especially on larger datasets. The results support using lightweight hybrid encryption to balance security and performance in smart healthcare systems. If anyone may have any question.
Yes, Nada, good presentation. I just want to know that you said that your system is a lightweight system. So how do you compare your system with the standard models that are there for encryption? Yes, am I audible?
Sorry, can you repeat the question?
My question is, you said that your system is a lightweight system. So how do you compare it with the standard systems that are there at present for encryption in the IoT environment?
I compared by using time consumption, CPU usage on my operating system, and I used also different virtual machines with minimal resources to prove these results.
So is your model scalable?
Yes.
Okay.
Thank you, Ms. Nada and
Hey,
Dr. Abdullah.
Yes,
I
Miss
don't-
Nadal. Hello,
Hello.
Miss Nadal. Thank you for your presentation. I have only one question. So, what were the key factors that led you to choose SPEC over other established lightweight encryption algorithms?
Okay. I made a comparable study and sorry, I made a comparative study among different algorithms such as LEA, Simon, Present, and SPEC. In this comparative achieved the most effective way. And I also review many articles that showed that the spec is still or remain the most effective algorithm in software.
Thank you.
Thank you, Ms. Nada, for your presentation. And Buga session chairs for your questions. Up next, we have Harvati Hashim presenting AI-driven predictive analytics for identifying at-risk learners in online ESL courses.
Okay, thank you, Ms. Moderator. May I share my screen?
Yes, please.
Okay. Right, give me a moment. Okay, do you see my screen now?
Yes, it's visible.
Okay, so if I were to use this display feature, are you able to see?
Yes.
All right, okay. So thank you so much, Ms. Moderator, and to our two professors, panels of the session. Hello and good day, everyone. I am Harwati Hashim. On behalf of my co-authors, Chong Seng Tong, Ahmad Zufri, and Heng Zi Hu. Today I will share our study on AI-driven predictive analytics to identify at-risk learners in online ESL courses or English as a second language using LMS traces. In short, we are looking at simple, interpretable LMS behaviors which can flag disengagement early, so lecturers can intervene with supportive and transparent actions. But we are going to put a disclaimer here that we are not trying to do any surveillance. So online ESL gives flexibility, but dropout and disengagement still happens. And lecturers often notice risk late after missed work or poor test performance. Learning using LMS needs repeated practice and interaction. So when learners go quiet for silent weeks for some time, that is a meaningful warning sign. And the opportunity is that LMS logs provide continuous low-cost signals like SAS patterns and submissions behavior. So we can detect drifts earlier and respond with human-centered support. And what we are looking at is the LMS that we are using at our university, which is University Kebangsaan Malaysia. And our guiding stand is clear with regards to this research, which is we are trying to look at how this AI predictive model could support learning, not surveillance instead. So our aim is to build and evaluate predictive model which is able to classify learners as at risk versus not at risk using teachers' meaningful LMS interaction traces, and to propose a workflow that course teams can pilot. We are looking at the learning analytics, which is available in our learning management system. So with that, we intended to answer 3 practical questions, which LMS behaviors signal disengagement risk, how accurately can common models classify risk, and how do we translate predictions into ethical human-centered interventions. So we also frame this through self-regulated learning or SRL, where LMS traces approximate planning, monitoring, persistence, and follow-through so that analytics stays pedagogically interpretable. So looking at our data set and workflow, here's the workflow. We're looking at model logs, engineered features, prediction, as well as early support. So our data set comes from our LMS system, which is ESL course based with 23,893 log events linked to 120 learners after removing system and instructor events. We're looking at only learners' engagement with regards to the activity in the login events. So we engineered lecturer meaningful features or teacher meaningful features such as content access, the total views, task engagement, assignment events and submissions, time behavior with regards to active days, activity span, events per active day, as well as social traces with regards to forum posts, which were very low. And I have forgotten to highlight that these 120 learners are those who were in year 1. So they are junior students. And then we feed predictions into a simple lecturer or teacher run support routine, which are nudges, feedback, and check-ins. So because great outcomes were not available in the LMS export, because we are looking at more of students' activity and engagement, so we operationalize risk using engagement. So in this study, at risk is defined as the bottom quartile of overall LMS activity, meaning that the lower the students' engagement is, they are at risk. Using this threshold, total events similar or lower than 154.25. And this year's 30 at-risk learners, which are 25% in total, and 19 not at risk, which represent 75% of the overall 120 students. So crucially, this is an early behavioral flag. Although it is not a great prediction, the intent is to prompt supportive outreach early enough to matters or to probably plan for intervention. So if we were to look at the engagement snapshots with regards to the LMS feature table, so the descriptive snapshots shows large variability, meaning learners engage very differently We can see two key patterns stand out. One is assignments dominate activity, which making submissions a strong behavior signal, probably because of the requirement of the course where lecturers keep on reminding for the students or learners to submit whichever tasks assigned to them weekly, and then those tasks would be discussed in classroom, more in the context of flipped learning. So therefore, assignments dominate the activity. And if you were to look at forum quizzes are near zero, so social traces contribute little in this specific course design. However, we also notice that probably due to the feature of the LMS where it is not that convenient for lecturers to post a lot of forums because of the engagement features is not as convenient or as preferred by the learners. So rather than using many complex signals, we focus on a small set of robust, interpretable behaviors that reflect consistent participation and follow through. So if you were to look at the predictive modeling, we tested several common models using LMS features, which are logistic regressions, random forest, gradient boosting, and a neural network. So we use 80-20 train test split and reported standard metrics, which are accuracy, AUC, sensitivity, specificity, precision, and F1. So our interpretability stance is important. We prefer transparent features so lecturers or teachers can connect the predictions back to teachable behaviors, especially through the self-regulated learning lens. And the results are, if you were to look at the detailed performance that we reported in random forest results, the accuracy of 0.86, AUC 0.89, sensitivity 0.82, specificity 0.88, and precision 0.80, and F1 0.81. So the confusion matrix summary shows practical usefulness, where 26 out of 30 at-risk learners correctly identified. So we are trying to look at whether the early predictions are 30 for at-risk and 90 not at-risk are rather accurate, and we found out that based on that interpretable models, and we tested the performance, and we found out that yes, 26 out of 30 are at-risk learners. And for the 90 not at-risk learners, there are 79, which are correctly identified out of 90. So we acknowledge that in the abstract, logistic regression is reported as very strong. So accuracy of the predicted model is 0.958 and AUC is 0.991. So we actually tested multiple models, and interpretable baseline performed extremely well, while random forest is highlighted for robustness in the detail sections. So if you were to look at the indicators or actionable support, the most important part is where lecturers or teachers can do with these signals, where the top indicators highlighted active days, class total views, which are consistent and frequent, whereby assignments, submissions, or events, which is something that need to be followed through. Activity span and events per active day is considered steady rhythm versus forum posts were negligible here, likely due to cost design and low usage. And also, as I mentioned just now, probably because the preference of the teachers or lecturers, which the features of the LMS itself is not preferable or convenient for the teachers and the learners to somewhat operate the forum features. So we propose a light touch support, which are a nudge after missed submissions of sudden drop in weekly presence, and also short check-in, like for example, what is the next step in of identifying at-risk learners, as well as a weekly checkpoint and micro tasks to stabilize engagement with them. Timely formative feedback and resubmission opportunities is also important, where teachers from time to time or lecturers from time to time, like a weekly basis, or keep on regularly checking whether submissions or feedbacks need to be given as students submit their assignments in the LMS system. So that would then change the students' behavior to ensure active engagement. Same goes to self-regulated learning coaching prompts to support planning and persistence. So ethically, we emphasize that it is to be transparent about what is collected and why. So it keeps learners in the loop and use predictions to offer helps, but not penalties. What we're trying to look at here is not surveillance, but rather providing support on how to ensure learners are engaged in the learning management system. So as a conclusion, we conclude that LMS engagement traces can flag risk early, often before grades reveal problems, because looking at how the approach, or what we call as outcome-based learning at universities level, so it is very much of self-regulated learning approach, and therefore we would try our very best to avoid problems in terms of summative performance. So a small set of interpretable features is highly informative, and we would like to conclude that predictive analytics is most valuable when paired with lecturer-centered support routines. So limitations include a single course data set, because in this particular study, only one course was investigated, and the data set used is reflecting only one cohort of learners, which are 122 students of year one, and an engagement-based risk label. So the next steps would be probably to validate whether the models that we are looking at validating using multiple forces, adding contextual variables, especially in terms of learners' behaviors, and evaluating interventions experimentally, which we did not do that in the context of this current study. And whether this kind of outreach or interventions or preventions could improve retention and outcomes, especially learners who are in year one, so that we could somewhat support them in terms of online learning, as well as encouraging or enforcing them to be familiar with self-regulated learning. So with that, I thank you and I welcome questions. Thank you so much.
Yes, thank you for a nice presentation. I have two questions here. First is, please tell me what are the most influential features that for the risk-based learners? And second is, how did you decide to choose the models that you have chosen for this prediction?
Okay, so one of the most influential features is the in terms of the activities, chosen activities by the learners, where we can see that, as I mentioned just now, assignment is one of the most uh, task engagement with regards to the students' learning events, probably because of how assignments and assessment were enforced with regards to teachers monitoring in classroom setting, and therefore that has become one of the most focused influential behavior with regards to learning engagement in the LMS system. So if I were to answer question two, in deciding the models, actually we look at four types, which are logistic regressions, random forest, gradient boosting, as well as neural networks. And this is basically were chosen based on our literature review, as well as findings from certain studies. Although if I were to mention that, of course, these four models go across different nature of courses. And what we have decided here is to look at, because these learners are education background, and they are teaching English as a second language. And that would be one of our limitations, whereby it is yet to be tested whether the four modules are equivalent with regards to the nature of the students' program. But basically, the four modules were chosen based on our literature review, Prof.
Okay, thank you for the answer.
Thank you so much, Prof.
Okay, Ms. Sarwati, my question is, among the most influential features identify the resource views, submissions, and weekly engagements. Did you observe any notable interaction or patterns that help explain students' disengagement behavior?
if I get your question right, Prof, whether we observe disengagement or
Behavior, yeah.
behavior, yeah. Uh, as I mentioned just now, among all factors or activities or events that were reported in our study, we found that forum uh, is has the lowest engagement features, and as I mentioned, probably because of the features of the learning management system itself is not as um uh, yeah, because we have very much familiar with like open learning courses, MOOC, or like for example, with more convenient features as compared to what we have at our university. And that foreign features is very much of like a two-way interaction between two students, and the way the chat is arranged is not, I would say, interested to look at. So therefore, that would be one of the influential factor with regards to the features of the forum itself. And that would be something that we actually suggested to our digital department, whereby try to improve. And that would probably be influenced by the new generation of learners and how they see engagement, because they are very much convenient of the how social media, social networks engagement features should be embedded into learning management system as well, Prof. So that's what we actually concluded from the study. But we, of course, we look forward to get more rich data from the interview from the students, because this is very much of predictive of learning analytics, and we have yet to get data from the students themselves. Probably in terms of semi-structured interview, that will further enhance and validate the findings of the study. I hope
Thank
that
you.
answers the question, Prof. Thank you so much, Prof.
Thank you for the presentation. Next, we have Chinmay RM presenting Foxtrography versus Digital Forensic, a comprehensive review of synthetic media generation and detection in the Gen AI era.
Hello everyone. Can I share my screen?
Yes, sure.
Okay. I will have to leave the meeting and join again. Is that okay?
Just make it quick because you only have 12 minutes for the presentation.
Yeah. I'm back. Okay. Is my screen visible?
Yes, it's visible.
Okay. So, 1 second. Right. Okay. Yeah. Hello everyone. I'm presenting a work titled Foxtrography versus Digital Forensics, a comprehensive review of synthetic media generation and detection in the Gen AI era. Our research explores the co-evolutionary arms race between AI that creates hyper-realistic fake media, which we call deep fakes or foxtrography, and the forensic tools designed to catch it. I am Chinmay and I am presenting on behalf of our co-authors from PS University, Bengaluru. So before we look at the data, can you look at these two images? Can you tell me which one's real and which one's a deepfake? In the Gen AI era, our eyes are no longer reliable witnesses. This indistinguishable quality is the catalyst for the forensic crisis we are discussing today. The one on the right is a deepfake. So we define the relationship between synthetic media and forensics as a co-evolutionary arms race where every advancement in generation creates a new hurdle for detection. And every new detection shield encourages generators to evolve sharper swords to bypass them. Our study highlights that this race is asymmetrical. While detectors are often reactive and model dependent, generators are becoming increasingly general and resilient. The generation taxonomy. To defend against deepfakes, we must first understand their anatomy. Our research categorizes these manipulations into 5 tiers. Identity swap or face swap. This form of deepfake is very common and involves swapping the identity of a person in a target video with that of a person in a source video. Typically, this is done using an autoencoder framework. Face reenactment, expression swap. This technique produces a digital puppet which imitates head movements, facial expressions, and speech patterns of the source actor to the target individual. Usually, this is carried out through the combination of GANs and neural rendering methods that perform landmark manipulation in a highly realistic manner. Attribute manipulation. This method modifies certain aspects of the face like age, gender, or hair color without changing the person's core identity. Modern diffusion models and architectures like StyleGAN are excellent at this task. Entire face synthesis. This is the creation of a whole new photorealistic human face that no one has ever seen before. GANs and more so StyleGAN were instrumental for this activity. Talking face generation. This method synthesizes the video of an individual speaking from a speech input. These models learn subtle relationships between speech phonemes and related lip movements to produce realistic and synchronized talking heads. The realism of foxtography is driven by two main paradigms: generative adversarial networks known as GANs and diffusion models, as detailed in Table 1 of our paper. GANs involve a zero-sum game between a generator and a discriminator. While they offer fast inference, they're often unstable and prone to mode collapse. Diffusion models, emerging as a new reign, use iterative denoising to reconstruct images from Gaussian noise. Though they are computationally more expensive to train and slower at inference, they offer superior photorealism, higher sample diversity, and unparalleled controllability via text-to-image synthesis. Generalizing these models to video adds the challenge of preserving frame consistency. Training large video models from scratch is computationally prohibitive. Instead, we see a pattern of transference, where 2D image architectures are inflated into 3D spatiotemporal designs. Leading systems like OpenAI Sora and Google Veo have transitioned from CNN-based UNets to diffusion transformer architectures, enabling the generation of coherent, long-form video foxtography. On the defense side, detection has traditionally relied on identifying fingerprints or artifacts. So spatial analysis uses CNN-like exception net to catch pixel-level discrepancies. Temporal analysis uses RNNs and LSTMs to detect unnatural flickering or blinking patterns. However, the core weakness is that as these generators strengthen, they explicitly learn to eliminate these artifacts. This makes artifact-based detectors inherently fragile and prone to becoming obsolete as soon as a new generator is released. The new frontier, which is semantic and physical inconsistency. Because pixels can be faked, we must move towards universal inconsistencies. One of the most promising areas is geometric and physical inconsistency. Research reveals that even the best models struggle with projective geometry, resulting in errors in shadows and 3D perspective. Frameworks like DBAGNet are leading this shift by combining handcrafted geometric signatures based on the golden ratio with behavioral blend shapes. This tests the model implicit understanding of the 3D world, which is much harder to fake than a simple pixel pattern. The most critical finding of our review is the generalization crisis. As shown in Table 2, detectors that achieve nearly perfect scores as 0.98 AUC on scholarly benchmark collapse catastrophically when facing in the wild data, which is taken from the Deepfake Eval 2024 dataset, which is a curated dataset of latest deepfakes collected from the internet and social media. For example, GenCon VIT drops by 48% to 0.51 AUC, and StyleFlow drops by 50%. In these real world scenarios, these state of the art detectors are performing no better than random chance, which is as good as flipping a coin to decide whether an image is a deepfake or not. This proves that we are currently optimizing for a threat landscape that does not exist in the real world. We also examine the roles of multimodal LLMs for a reasoning-based detection. As seen in Table 3, while GPT-4o demonstrates the strong zero-shot reasoning with an AUROC of 0.81, this capability is not universal. We found a scoring inversion in many models. Open source models like Llama 3.1 Vision actually perform below random chance at 0.48. This suggests that high level reasoning is currently an emergent property of massive scale proprietary models rather than a generalist categories of MLLMs. Because purely reactive detection is unsustainable, we advocate for a multifaceted approach. Proactive defense. Moving to content provenance standards like C2PA, this acts as a cryptographic nutrition label to provide authenticity at capture. Adaptive detectors, using meta learning to teach detectors to quickly adapt to novel, unseen manipulation techniques. Forensic integrity, integrating explainable AI tools like Lime and SHAP to make black box decisions interpretable for legal and forensic use. In conclusion, our review has traced the trajectory from GANs to diffusion models, documented the failure of traditional detection paradigms. The catastrophic 50% generalization gap on real world data proves that academic benchmarks must evolve. We believe the future of a resilient information ecosystem lies in combining proactive authentication with physical consistency analysis and forensically interpretable method. Thank you for your time.
Yes, thank you, Chinmay. So I think you have finished before your time. So it was a nice presentation. I'm just curious to know that which is the most challenging characteristics in the AI generated images that is difficult to detect.
The most challenging characteristic would be laws of physics, I believe. As of now, most models that are trained that are like amazing when it comes to academic benchmarks were trained on artifact-based detections like blurry pixels and small inconsistencies. But when it comes to videos or actual laws of physics, these models fail terribly.
Okay. So is there any solution to this, or have you thought about it?
As outlined in our conclusion, we must use more methods like combine physical inconsistency to analyze the information ecosystem. So as of now, I believe there are no methods, and hopefully the field evolves to integrate these data sets, the most recent data sets, into our academic field to, move towards physical inconsistency. Right now, I believe it's not a field of interest.
Okay. Thank you.
Okay. My question is, in your analysis, what remains the biggest technical barrier preventing deepfake detectors from generalizing effectively to unseen manipulation techniques?
So the main challenge was, like I said, these state-of-the-art models were trained on outdated data, which have simple artifact inconsistencies. But as you can see, the data taken from the most recent internet and social media uh, bypass these artifact inconsistencies and move on to something further. So that is the main reason why these benchmarks, why these models fail when it comes to recent latest deepfakes.
Okay, thank you.
Thank you.
Thank you, Ms. Shinmay, for that presentation and your session shows for questions. Next, we have Dina Sekar Whisperita, presenting human-computer interaction and ICT as catalysts for post-COVID transformation in the international medical tourism.
Thank you, Sanskriti. And then thank you for helping me sharing the presentation. Good evening, everyone. Sorry, good evening from Jakarta. I want to say good evening from Jakarta, Indonesia. Here, almost 8 p.m. Okay, let me start my presentation. The title is Human-Computer Interaction and ICT as Catalyst for Post-COVID Transformation in International Medical Tourism. Me, Dinaskar Fusparati, and then my colleague from Binus University Indonesia, Handi Martinus, and this is also a collaboration research with my colleagues from University Utara Malaysia, Eshabi Mustafa, and also Hidayat Ahmad Rizwan from University Technology Mara, Pulau Pinang, Malaysia. Okay, the introduction. So Malaysian medical tourism and patient flow. So here I'm trying to explain about the Malaysian context from first, where Malaysia recorded a very remarkable growth, which is 15% in medical tourism revenue into 2023, solidifying its status as a premier global healthcare destination, specifically in Southeast Asia. And then in Malaysia itself, Penang served as the leading hub, where accounting for approximately 40.7% out of national medical tourism revenues. And in Penang, this research focused on Island Hospital, which stand out as a private provider from Malaysia Flagship Medical Tourism Hospital, kind of an organization in Malaysia. And then the very interesting part is about this Indonesian patient, because demographic side, we can see here, this Indonesian constitute the largest international patient group, which is 60 to 65% of Malaysia's total medical tourist flow. Most of them go to the specialties include the cardiology, oncology, orthopedics, and about these fertility treatments. It is very famous in Indonesia, where a lot of patients with those four issues will go to Malaysia, especially Penang. And when COVID came into this world, so we have this called pandemic disruption. The mobility restriction halted the cross-border patient travel, severely impacting the medical tourism revenue and continuity of care, because a lot of country closed the country, also Indonesia, where the Indonesian government closed all the airports, and then I think Malaysia too, and a lot of countries do the same action to prevent this COVID-19 pandemic. So the crisis exposed significant vulnerabilities in trust building, because then we were forced to use this technology in terms of communication. And then the face-to-face interaction also became impossible. So this forced everyone, including this medical tourism, to have this digital shift. So a lot of people have to do this rapid adoption of telemedicine, online consultation, and remote follow-ups became essential as a survival strategies. Integration of familiar tools like WhatsApp and live chat enable real-time patient engagement across border. So the key challenges for this industry is about the trust deficit without physical presence, and then digital literacy gaps, and also the hesitancy toward remote diagnosis, because medical really needs trust between the patient to their doctors. And then distance also become the issue for this industry, though Penang or the Malaysia hospital are very famous here in Indonesia for their treatment, and then the success story are very famous here. So let's see the new opportunities where then patients showed higher willingness than to adapt this digital health when systems were reliable, user-friendly, and culturally responsive. So research questions are about the trust building platform. How do ICT and HCI enable digital platforms to facilitate the trust building in this international medical tourism context? And then about the patient perception. How do patients and family perceive the usefulness, ease of use, and cultural responsive of these digital communication tools in mediating continuity of care, because though Malaysia and Indonesia are quite familiar, but in terms of language, where for Indonesia, English is not our second language, is still foreign language. So just few percent of Indonesian people can speak English, while in Malaysia, English is very common language among the community. Also in Penang, the Mandarin also used as a what do you call common language too in Penang. And then though one of the province near Malaysia, which is the North Sumatra, Medan especially, they use also Mandarin, but they use a different accent. So these cultural gaps also become one of the challenges. And number 3 is about the transactional communication, where how does transactional communication characterized by reciprocity, feedback, again, cultural sensitivity, operate through ICT mediated interaction. This is about the trust, this is about the language, this is about the culture, and also the transportation, also about the religion, because though Malaysia is Islamic country and Indonesia also Islamic country, but the environment is different, because in Indonesia, most of the people are Muslim. Even though now I think Indonesia become not become number 2. Before was number 1 or number 2 as a Muslim country. So talking about the food, talking about the environment, maybe for those old people that are looking for medical treatment, it maybe become the challenges. And number 4 is about the institutional integration. So the question will be, what institutional support, technological strategies, and design approaches enable or constrain the effective integration of ICT and HCI in fostering technology as a mediation trust. So the theory used for this research is the technology acceptance model, to know about the perceived usefulness, how the patient believe that using these digital tools will enhance the healthcare experience and outcomes, the perceived ease of use, the degree to which digital platforms are free of effort, intuitive, and accessible, and also external enablers like the infrastructure quality to help the patient for this technology adoption. And number 2 is the transactional model of communication. Since this research also based from a communication degree or communication major in Binus University, so we really also focus on this communication. So this transactional model of communication theory will help the research to analyze the dynamic reciprocity, where the communication as a simultaneous sending and receiving process, where meaning is co-constructed, where this language, this culture will really influence the communication interaction between the patient and the doctor. And then number 2 is about the feedback loops. Continuous interaction allowing for clarification, reassurance, and emotional connection, because medical is not only one time coming, but it's continuity of checking, maintenance, and also feel to have this secure of healing themselves. And again, the cultural sensitivity, because it's between 2 different countries, though Malaysia and Indonesia is very close, but again, this culture is very different. So if we make a summary of these 2 theories, it becomes technological acceptance plus the relational communication, making this technology mediated trust. So the methodology that we use here for this research is qualitative case study, where we make the Island Hospital as our case study, because this is the leading medical tourism provider. And then we focus on the in-depth semi-structured interview as our data collection. Also, we did direct observation. We went to this hospital, observing all the activity over there. And then we also analyzed their Island Hospital digital platform. We interview Indonesian patient in Island Hospital directly. And then we also interview the family members who accompany this patient, and also those family members who had the experience of their other family members having this medical treatment in Island Hospital. For direct observation, sorry, I haven't finished Sanskriti, sorry. For direct observation, we also look at the, oh, yes, this one, sorry. For direct observation,
Excuse me.
Yes.
I'm so sorry. This is
Timing? Sorry. Okay,
oh
let's
yeah,
go to finding.
you have 2 minutes left.
Okay. Let's go to the finding. So I think let's go to the finding to make it fast. So this platform enable trust, the website transparency, where there is a very clear about the pricing and then the doctor qualification and then the treatment pathway. They really explain everything in their website. And then the multilingual interfaces, where they also use what we call the over a lot of languages over there, including Bahasa Indonesia and the English one, and then the Malay one, and the Mandarin one. So they really try to make this Indonesian patient feeling comfort using these technology tools. And also the perception of digital tools, where the familiarity drive adoption. Tools like WhatsApp, they also have this Indonesian WhatsApp number, and then the chatbot that really communicative to the people of Indonesia to interact, asking questions, and a very fast response from them. And also the continuity of care, where they also the patient who had this treatment in Malaysia, when they back home in Indonesia, they also still can have this communication with the staff, and then they also can make appointment with the doctor through WhatsApp, where they're still in Indonesia. So when they come to the hospital, it's all already set, including all the accommodation. And then number 3 is the transactional communication, where as I said, the two-way dialogue is very strong. So this is really help to develop the trust for the patient and including the families, because usually the patient, not all, but half of it are those old people. So sometimes the children of those patients are really helping the parents to have this medical treatment. And co-construction of trust, this empathy, personalized responses in digital chat really help them to feel comfort, secure, and believe with everything offered by the hospital. And the system integration, number 4, where they also make sure the standard from the Malaysia government, and then they also have a very what do you call it, implementation of user-centered engineers design strategies. Yeah. And then one thing is that they also use their agent, where located in Indonesia in 4 main cities, which is Surabaya, Jakarta, Medan. Three cities: Jakarta, Surabaya, and Medan. So they know really where the patient located. So this human and also technology agency, communication agency used by the hospital really help the patient. And then next. So this is so I make this conceptual model where the technology mediated trust in medical tourism. If you see here, the ICT and HCI infrastructure, having all the tools, and then with 2 different way of communication, helping the patient and then also the family, which equals to the trust outcomes. Yeah, reduce uncertainty, patient confidence, and then institutional credibility for sure, because this word of mouth promotion is very effective, mouth to mouth between the patient to other maybe friends, other family members. So this really helpful for this hospital to get a very good promotion. And then this continuity of care, they really care about the patient, and then become the strategic impact. As a summary, yes, thank you, Sanskriti, for the reminder. Next slide, last one. The summary, so for practical implication, so the design for trust is very important for the patient. The responsive of cultural is really helping also the patient and the family consistency, and then the policy alignment, which is aligned with the government or the Malaysia government policy. Though this research also have limitation and also need to have a future research direction. Thank you.
Okay, thank you.
Sorry, it's too fast.
Yes, thank you, Dina. So my question is, the system that you have developed is only means the adoption of the system was only post-pandemic, or it is still going on? And
Yes,
yeah,
yes,
and
it is.
it is only Indonesia specific.
This is still going on and it's open for everyone because it's very public website, public chat box. But then again, 90% of their international patients are coming from Indonesia.
Okay, because then there will be a communication barrier, no? So you have addressed only with respect to Indonesia, I guess.
Yeah, this focus on Indonesian patient, why this Indonesian patient really trust island hospital and then become the 90% of the international patient.
Okay, so if you want to scale the application, what changes you will have to do?
Yeah, I think I want to have another hospital in Malaysia to make sure, or I really want to know whether Penang is the one become the favorite of Indonesian patient, or there is any other hospital in Malaysia. And the research result, I think, would help Indonesian government. I mean, why their people have more trust in a Malaysian hospital than their own hospital. So it's very good lesson learned for us too, Miss Fidula.
Okay, thank you.
Thank you.
Okay, thank you. Based on your findings, what challenges do you foresee in scaling culturally responsive digital communication practices across different hospital system or patient population?
Yeah, I think the challenges are because I met a lot of old Indonesian patient over there, and then when it became interview sessions, they are reluctant to answer the questions, and so it's really hard for me to have more information from them. So the interview happened using the mediator, which is their children. That's my challenge doing the interview, and also with their condition. I had this main Indonesian patient, a male Indonesian patient with a broken leg. So when I did the interview, the wife looked very, you know, uh, annoyed with my present over there. And then also when using this website, I know that technology is not quite familiar for those people from province outside Jakarta, because most of the Indonesian patient for Malaysia, most of them coming from those provincial close to Malaysia, like the Sumatra Island, the North Sumatra, and then South Sumatra, those areas. So compare with Jakarta patient that came to Malaysia, the language is also challenges.
Thank you.
Thank you.
Thank you, Ms. Dina, for your presentation. Cheers for the questions. Now we have Isaiah Essien presenting Real-Time Epilepsy Monitoring System, leveraging computer vision and Internet of Things within a local area network.
Hi, everyone. Good afternoon from where I am, and hello to everyone. Thank you so much, Chair and moderator, and every attendee. I'd like to share my screen now. Please, can you hear me?
Yes, you're audible.
Okay. Thank you. I'm trying to share my screen. Okay. Okay. So on behalf of my co-authors, Samiratu, Toso, Marvin Ogori, and Andrew Jennings, I will be presenting to you today real-time epilepsy monitoring system using computer vision and Internet of Things within a local area network. Epilepsy is a neurological condition that is characterized by repeated seizures, most times violent seizures, due to abnormal electrical discharge in the brain. And as of the time of making this research and conducting research on this project, there is no cure, but epilepsy can obviously be managed. And one of the management criteria is actually require the patient to be most times monitored, most times cared for, including having a alert system to enable people rush and help them when there is an episode. But there is a very persistent problem in Africa, especially sub-Saharan Africa, whereby Africa holds about half of the world's epileptic population. According to a study by the World Health Organization in 2023, there is an estimated 50 million people in the world living with epilepsy, and about 25 million of them are in Africa. Shockingly as well, about 70% of those people in Africa do not have any access to care, and do not have treatment, do not have any alert system. Now, this lack of timely alert system and care actually contribute to the highest, Africa having the highest mortality rates in epilepsy epileptic patients, so to say. And the reason is this way is because most or some of the available epilepsy systems, most like, let's say, Zisho alarm watches that actually can be paired with smartphones, they are not really enough to kind of like give timely alerts in context, especially when there are violence issues. A couple of them do not even actually operate in Africa. Some of them are not even shipped down to Africa. And every year in Africa, 15 out of every 1,000 epileptic patients die due to lack of timely intervention. So this creates a very big question. What can be done? Obviously, there have been a lot of should I say, projects and research in the past that actually propose solutions. One of them is the EEG, which is electroencephalography, which is the gold standard of measuring electrical impulse in the brain using electrodes. But most of these machines are not even in Africa. And still, people who actually suffer with this condition really do not have enough money for such care. So what is needed is to have a solution that is actually vision-based, something that can actually help these people and to reduce the mortality rates by giving timely alerts and intervention so that people can rush and help people suffering with this condition, especially when they have epileptic episodes. So we are presenting a solution that consists of a very straightforward architecture here, where we are using computer vision, and we are actually operating using a live camera. So we want to see a way to measure or give alerts by the camera actually viewing the patient, and then sending signals from the camera to the model for inference, and then a model running on the local area network can process that signal and actually infer if this is a seizure episode and if it's worthy of an alert. If it's worthy of an alert, then it sends a signal to the buzzer, and the buzzer actually rings an alarm, signaling neighbors or people to rush in and help. This is because most of the mortality rates in epilepsy actually arise due to a lack of timely intervention when there is an epileptic episode. So the system is simple. It's a real-time, no-contact seizure alert system that uses basically two technologies. One is the core computer vision, which actually uses a standard camera to detect convulsive seizures, and then Internet of Things, where we have things like a Raspberry Pi or any other kind of edge device that can actually host a model and run and operate over a local area network. And then a buzz as well, still part of the Internet of Things system to trigger an alert. So the data here is a very interesting part of the project, because currently there are no available video epileptic data. Nobody would want to put out a video of them having epilepsy in the net. So it's really hard to find this kind of data. But what we did was that we were able to source some of the data from internet by having, some of the short clips of epileptic seizures, we pre-process this data by trimming, removing some of the excessive noise. And also, we were able to generate ethically grounded data set by having neurologists and epileptic doctors to help um, the creation of data set by people simulating seizures, and this video is being recorded over a particular control time frame. And the result was that we were able to get about a good number of data, in this case videos, short clips actually, and those short clips were actually not processed directly. We use a Python library called MediaPipe. MediaPipe is a Python library that enables people to kind of like extract poses or landmarks from videos and pictures. So when we are processing the videos, we are not directly sending any of these videos to the cloud. We are actually just extracting the post landmarks, as we can see here. And using the formula on the screen, we were able to generate post landmarks for 33, extract post landmarks, sorry, for 33 landmarks of the human body, starting from the eyes, the limbs, the hands, and even the torsos, which are actually areas of the body that are very obvious when people are actually having convulsive seizures. And we were able to come up with a 132 dimensional vector. And all of this we actually stored in a CSV file where we now use to train our model. At the core of this system is the model, which I'm going to talk about briefly. We choose a custom lightweight transformer architecture combined with a multi-head attention because we wanted to kind of capture the spatial-temporal patterns that actually are being exhibited in or during seizures. Most times, seizure is a spatial-temporal event. It happens convulsively and occlusively over time, and an epileptic episode can last, let's say, between 5 seconds in most cases to up to 90 seconds, and that's enough time for people to get hot or even actually, worst case scenario, die. So we are trying to see if there's a model that can be deployed. One, a local area network doesn't need a lot of dependencies, doesn't need GPU, can run independently and make predictions. So we went with this model design. Obviously, we tested other models to see which one works. We tried a couple of architectures, including recurrent neural networks and long short-term memory networks. But what we came up with was that most of those were either overcomplicating things or they were actually missing the exact seizure events. But with the model we had, we were able to come up with an overall result of 93.9% accuracy over all the seizure sets, and sorry, over all the data sets as well. But then specifically for the seizures, we were able to have a precision of 93.2% or 93%, and then a 90% recall, whereby our model was able to catch most of the seizure or epileptic events. And here on the right side of this slide is a sample confusion matrix that was actually calculated on the test set of our data. But then it didn't stop there. What we are building, what this system is actually doing is trying to create a local area network centric system that operates entirely without an internet. So users does not need to worry or do not need to worry about the availability of internet. This can actually be connected over local area network on the same LAN router that is being available. And some of the hardware we use were the Raspberry Pi, which is like the brain of the system. That is where the model is stored. That's where the inference is being done. And the IP camera, which is like the eyes, which actually sees or actually monitors patients in real time and then sends signals. And when these signals are being processed and inferred as epileptic episode or events, then the buzzer sounds an alarm, which I'll demonstrate in just in the next slide how it works. And it is designed specifically for areas with low connections and maybe poor usage of internet as well. And so this is just a short clip of how it works in a few seconds. All right, so this is what we were able to come up with. And our system did not just stop at the notebook. We didn't just create these models and create this system and test around with simulations. We were able to test with real patients who actually consented that this system should be tested on them. And over a period of 3 days, we were able to record 15 episodes, each of them lasting an average of about 90 seconds. And out of those 15, we were able to detect about 12 of them, which is an 80% field testing accuracy, which is good for what we're trying to do. And as we could see on the short clip, the period between the seizure event to when the buzzer is being triggered is about 2 to 6 seconds, which is a good time to give enough alerts for people to rush and help people that actually have seizure episodes. What we learned in this project was that the camera view as well, or the occlusions can be a very key factor in the performance of this system. For instance, we know that we need to have some bright lights at least to be able to have a functional camera output to the model or input to the model, sorry. And apart from that, the distance between the camera and the patient has to be carefully structured. But still, we were able to have some very good results despite the distance, especially in a room, a standard room size area. Some of the limitations of this work were one, technically the system
Excuse me. Sorry to interrupt you,
Sorry?
Isaiah. This is just a gentle reminder that less than 2 minutes are left for your presentation.
Okay, let me just finish the slides. Thank you. The system performs dependently on clear camera view, which I just spoke about, and it could detect accurate body landmarks when there is no obstruction on the camera. This system is not yet clinically tested. I have to stress this out. It is still in development, as we could see, but further on, we would want to go full scale to test how the system is working. And this does not claim to replace the clinical gold standard. This is just a work to see what can be done, especially in areas that have lacked to all the gold standard options. And ethically, everybody that participated in this project or research project actually gave their informed consent. So nobody here was actually being used under duress. Patient is anonymized, as we could see. We are extracting post landmarks and we are processing everything over the local area network by design. And the system, if you want to set it up from scratch, costs less than $300 compared to some of the available epilepsy options out there, like the smartphone and smartwatches, which cost up to thousands of dollars in most cases. So this is the work. This is perhaps one of the first in the sub-Saharan region, and the future work would include clinical testing and beta data incorporation. Thank you so much on behalf of the African Leadership University, Rwanda. We say thank you to ICICT for giving us a platform to present this project. Thank you.
Yes, thank you. The topic is very nice, interesting. So this is in the prototype stage, right? The system that you have developed.
Yes, most likely. We just have the first prototype, which I shared on the clip.
So, yes. So how do you plan to overcome the technical limitation that you have mentioned in your slide about the limited camera view?
So what we plan to do with that is we can't exactly rule that out because definitely when the camera does not have light, it won't be able to capture. But we plan to incorporate a multimodal system in the future where we can, put some sensors that can actually detect or, detect vibration, especially when there's no light. So we can actually still have a system that works both when there's light and when there's no light.
And how does your system clearly differentiate between the seizure movements and the normal movement a person does?
So most of the normal movements are rhythmic. Even if someone wants to shake their body, there is a rhythm that we can actually trace, especially when we're doing data pre-processing. We observe that movements like jogging, running, or just random shakings are actually rhythmic, but epilepsy has no exact rhythm, but but can actually be traced due to the spatiotemporal patterns. So starting from the time it happens to the time it actually stops, which is the post-occlusive period of epilepsy, you can actually trace carefully or very distinct patterns that are there as well. So it differs, and we did test the system on random movements, and it did not really catch much of them. But then actual epileptic seizures were actually caught.
Okay, thank you.
Thank you.
Hello. This is my question. Hello.
Hello.
Yeah. Do you plan to incorporate additional sensing modalities such as accelerometer data or EEG signals to further improve robustness and reduce false positive in real world use?
Yes, that's perhaps what I just also said. Let me just give more insights on it. In the future, we plan to incorporate an extension of this project is currently ongoing where we are testing accelerometer and gyroscope, but these ones actually work specifically for Android devices. So there's also limitation there, but we plan to incorporate, especially for people that have very violent seizures that require 24/7 monitoring. We plan to incorporate sensors, maybe wearable sensors that are actually cheaper than the ones out there, just to see how this can be done, especially if they are living where the camera is not there to view them, or maybe when there is no light. So we plan to add these modalities in the future.
Thank you.
Thank you very much.
Thank you, Mr. Isaiah, for your presentation. Finally, we have Adil Vidhan presenting Skin Thermal Net, an AI segmentation-driven calibration framework for skin temperature estimation.
Hello, everyone. Do you hear me?
Yes, you're audible.
Okay, let me share my screen. I know I don't have much time, but I will make it quick as much as I could. Do you see my screen, guys?
Yes.
Okay, so in behalf of my colleagues and my co-author, today I'm going to present our recent research about the skin thermal net, which is an segmentation-driven calibration framework for skin temperature estimation. So let's start with some motivation. I think this is a very scare maps of our world, especially when we know that the
Excuse
number
me,
of,
sir.
yeah.
Sorry to interrupt you, but your slides aren't visible. Your screen is, but not the presentation.
Okay. Let me share my screen again. Okay. Do you see my presentation now?
Yes.
Okay, so I think again this is a very scary map, especially when you know that in 2020 that is the number of deaths is larger than 500,000, and overall, like a number of cases in Europe is around 300 cases like confirmed, and that is a very high peak of COVID-19 death cases, and it's about in the United States is about 103, and especially in Iraq is about 200,000 cases. So the general thought is how to manage these things is by using a thermal imaging camera. So as you can see, most of us is familiar how to use a thermal camera to point it out in our front head and to just measure the temperature. But this has a lot of limitation. For example, here is not very accurate. You have to locate it very nicely, and sometimes it gives a lot of false measurement, especially if we're wearing a cap or hijab, or our hair is like in front of our front head, or for a dark skin and light skin, that is a lot of limitation. So I would like to show you a video with a very high expensive camera in the airport and see the false alarm appear.
So as I approach the thermal imaging camera, it picks me up and it can see that my temperature is 36.45 degrees. But if I put a bottle full of hot water onto my head, bingo, it thinks that
Okay, so that comes in mind, like, okay, with a very high expensive camera, it make a false alarm because there is something in your front head. So let's do something else to use a very low cost camera to manage the high cost camera performance. So I was looking and then found a very interesting data set in March 2021, which are 142 persons, 36 videos in a different angles, and they use two different cameras. As you can see here, they use a RGB, the sensor, so the thermal sensor camera and RGB sensor camera to come up with a one of the most challenge problem is the calibration. So because two different cameras taking picture for the same person, so if we need to project this RGB and the thermal in top of each one, and we have a calibration. That's why we designed the first approach is to do unsupervised learning for a unsupervised camera calibration. We use a lot of computer vision tools, and we do two double stage of calibrations and the registration, and then we do something called a thermal phase extraction and then thermal extraction. So let's move forward for the data set. This is a sample of the video data set we extracted to frames, and then this is the thermal associated with the case. And then when you project these two images in front of you, you can see it's far away from the reality. So what we did a resizing the RGB image, and then we do some banding. We don't want to play with the thermal image because this is our ground truth. And then by some iterations, we project them on top of each other, and that's why in this case we have a very nice projection, but we don't stop in this area. We use a registration to do a pixel by pixel wise registration, but before that we do some quality metric like SSIM and correlation to make sure that our two images are calibrated by calculating the similarities between these two images. So you can see here by the SSIM, this is before the calibration, this is after the calibration. It's the same thing for the correlation here. You can see the correlation has been increased a lot. Sorry, but I have to move very fast because I have number of slides than usual. And then for the second stage, this is some samples from the data set. You can see here, this is the batting image, and this is the calibration thing. And also what we did this is the total data set, the whole videos of the data set. You can see here the calibration has been increased, the SSIM, and the coloration, the coloration as well. And then we come up with another idea. So we, from the RGB, we take the face, because it's very hard to some cases to detect the face from the thermal image, and then we projected this back to take the thermal face, and then from the thermal face we need to get a scan from the RGB. So but before we extract these images to 3 channels, and then we use a registration individually for each channel by the thermal image to make a very high performance of a registration and calibration. And then we combine them back to have a very nice calibrated RGB. And then from the RGB, this is some result from we use 6 different calibration registration method, and then based on the calibration, we coloration and the SSIM, we choose the highest one at the end. And then this is, you can see the 3 channels of the RGB image using the SSM similarity is higher than our first stage of calibration. So we remove the SSIM and above, and also the calibration, the coloration as well has been increased, which is a good indication that most of the images are calibrated in top of each other. And then what we did, this is also the data set in total. You can see in the blue is the unregistered and the the gray, yellow, and orange are the calibrated. We can see in most cases the SSIM and the coloration has been increased. And again, this is if we overlapped the red channel, green channel, and blue channels, and then based on that we combine them to have a let me go back a little bit to have the calibrated RGB. Why we need that? Because we need to extract the skin, and then from the skin we convert it to a binary, and then from the binary we multiply it with the original thermal, and then we have a thermal skin. In this case, what we do, we extract the average thermal temperature. We give as a good indication, not in just forehead or nose tip. And this is what the average total temperature. You can see this case is being sick because it's a red flag. And I'm gonna show you most of this is all the frames, and then we combine them back to one video. And you can see here, this is we compare our result with a front head and with the tip nose, and then we extract the temperature. We can see here for the tip nose it's stable, but it's an reliable temperature, while the forehead you can see it is fluctuated, while the average thermal phase is most stable and it is close to the reality. Also, this is another case, and you can see here even the tip nose is fluctuated a lot, but the average thermal is much stable. And in overall, this is the whole data set. You can see in the gray, it's almost stable with close to the reality, while in some other videos, you can see it's not a real temperature. And this is some cases that is being labeled in the sick and non-sick, and you can see the average temperature. Even though you can see here with the nose, that means this case is sick, and also this is about 6. You can see the temperature is close to 37, and this is the temperature here is already distributed among the chin. This is another cases, and this is the video for the final prediction. You can see it's more stable and close to the reality among all the frames. Sorry for being very fast, but I know it's we are tight over time. So thank you. Any questions?
Yes, thank you, sir. So, does your system work across all the skin tones? Will it
Yes.
give the same results?
Yes, exactly. We tried like about 400 cases. Each case is about 130 videos, and this is about close 100 million frames.
Okay, and can it be extended for further some medical diagnostics like fever or any other things?
Sure. Sorry if I didn't have a future work slide because it's about to submit to a journal, but we use a autoencoder model to change automatically which cases you want to discuss and classify, and then you just put the label, and you have to set up the temperature, and then the system will give you alarm about the different disease, different temperatures.
Okay, thank you.
Okay, sir. My question is, what technical challenges would need to be addressed to extend your system for simultaneous multi-person monitoring in crowded public settings?
Okay. I think before we design a deep learning model to let's say the first limitation was it is unsupervised learning, so you have to set up a lot of parameters to get a very nice calibration. But then an upcoming paper which is being submitted soon to the journal, we design a UNet model. We train the model about the unsupervised binary mask that we created. Then the deep learning, you just get the thermal, and you predict the binary mask. So in this case, we don't have any limitation because the model will predict the binary mask directly from the trained data set.
Thank you.
Thank you.
Okay.
Thank you, Dr. Adil, for sharing your work. That is it for all the presentations today.
Sanskriti? Yeah. You please continue, then I'll ask.
Oh, if you have a question, please go ahead.
No, ma'am. Actually, I had a small request that can you share the first slide, welcome slide with my name? I just wanted to take a screenshot.
Oh, sure. I'll do
Yeah,
that.
you complete first whatever you were telling.
Oh, okay. Okay, so I would sincerely like to thank all the authors for the excellent presentations. This was a very engaging session and for their valuable contributions to the session. I also extend my gratitude to all participants for being a part of this international conference. I hope this session was informative and insightful for all of you. On behalf of the ICICT team, thank you for your continued support during the 11th edition of ICICT, as well as all the previous editions. We look forward to welcoming you again for the 12th edition in 2027. All presenters will receive their digital certificates via email within 2 working days. The publication is expected to be available within 7 to 8 months. We kindly request your cooperation with the ICICT 2026 team during this process. I would also like to thank our session chairs, Professor Vidula Mishram, and of course, Professor Jamie Pulambirit for effectively chairing this session today. And as a token of appreciation from GR Foundation and partners, we present this to you.
Thank you, ma'am.
Thank you so
Sir?
much.
Thank you so much, ma'am, and really well presented all the participants. Thank you for your presentation.
Thank you, everyone. May I
Thank you so
please?
much. Thank you to all our participants and also congratulations and see you on the 12th editions of this conference. Again, thank you for trusting me.
Thank you, sir, for your kind words. May I please request everyone to please turn on your camera so that we can have a quick snapshot of the session? Thank you, everyone, for joining us. Have a great day.
Thank you.
Thank you.
Thank you, ma'am.
Thank you all.